The purpose of this experiment is to understand natural frequency and damping in a single degree of freedom system subjected to free vibrations. So we are going to do two different things here. First, we are going to try to understand the effect of stiffness and mass on natural frequency, and we are also going to try to understand how we can calculate damping. What you see here is the setup we are going to use to do so. So this is a plate which is fixed at the base, and there is a mass added to the top. This plate can be idealized as a cantilever beam which is fixed at one end and free at the other end. To derive the stiffness, we can calculate that stiffness as 3 times modulus of elasticity times the moment of inertia divided by the span cubed. And the mass we can measure. We are told that we are going to consider two different masses of 0.3 kilograms and 0.5 kilograms. And there are two different spans or lengths that we are going to consider, which would affect the stiffness, which is a function of span. So one span is 30 centimeters and the other one is 20 centimeters. We are going to subject this to free vibrations like this, and there are strain gauges on the plate through which we are recording the response under free vibrations, and the software program is able to calculate the measured frequency. You are expected to compare the measured frequency for the 4 different scenarios with the calculated natural frequency. From the strains, we get the displacement response, which is displacement on the y-axis and time on the x-axis. So the program calculates the natural frequency using that data, and we can also use it to figure out the values of damping as shown in your manual.
This is experiment 9, vibrating test. The test is set up as follows: 2 steel plates, one 30 centimeters in height, the other 20 centimeters in height. 2 weights, one 300 grams and the other 500 grams. This setup must remain motionless before conducting the experiment. This is the data logger of the strain gauge. It can read data from the gauge. Use this steel ruler to measure the free end of the steel plate. Use the programs read data and analyze data on the computer for this experiment. Before starting the experiment, make sure the steel plates are completely still. After your partner is ready, laterally push the 30 centimeter steel plate back 2 centimeters. Use the steel ruler on the side to measure the distance. Let go of the steel plate when your partner signals. After making sure the 20 centimeter steel plate is motionless, repeat the same process with the 20 centimeter steel plate. Switch the weights on the 2 steel plates and repeat the same process again. Launch Read Data on the computer, then press the green monitor button. The data you see now is from the strain gauge. After making sure the steel plate is motionless, press BAL Balance to set the strain gauge to 0. The steel plate should be motionless and readings from the strain gauge should be around 0. Ask your partner to move the steel plate back 2 centimeters. Then press the record button and ask your partner to let go of the steel plate. Record data for about 15 to 20 seconds. Then press the stop button twice to cease recording. Open Data Analyze program, then open the file test0096. Next, on the top bar, click Analysis, FFT Analysis. Then click Graph at the bottom right of the pop-up window. Go to Analyze Data Numbers and put in 8192 and select a section on the graph. Then click Execute. Press Save. Then click Normal Mode button. Go to the bottom left corner and box select to magnify. Next, switch to cursor mode. Use left and right direction buttons to find the peak value. Use the print screen function on the keyboard to print screen. Then minimize the window. Open Word and paste the print screen into the file. Next, open TEST0096 Excel file. Note, this column is the data from the strain gauge. Select around 4,000 data points, then graph it.